Well, that would be the like max if that was the first, but is it? Wait, I was trying to find where it was allocated.
Yeah, we're just looking at the.
We talked about the quiz.
I think this is. If you like, if you put it in the graph.
I didn't, I chose the other one not because I thought that was it, but yeah, well, no. I chose that because this is where like the slope, because if it's the second derivative, that's where. But is that, am I just mixing up that it's not, okay, wait.
Yes, it's the
not
first, yeah.
But I had the right idea.
Let's do new math. So last thing you guys learned, just before we forget, was how to do, like, you get parametric equations, and I taught you how to take dy dx, like the slope of those graphs, and then how to get the arc length, and then and that's it. And now this one is a big section, not because it's super hard, but because you know for sure 100% is going to be like a free response question on the test, which is kind of good news because now, like, if you learn this okay, it's not super hard, then that's hopefully 9 free points on the test. Because all free response questions are worth 9 points. Anyway, vector valued functions, they sound scary, but they're not. So earlier you guys saw in AB how we study like what's it called? Rectilinear motion. Like when a particle is moving on a straight line and it moves like this and then moves backwards and then it moves like this. But we know, like, most things in the real world don't move like this on a straight line. They move like this on like a plane, like on the floor in 2 dimensions. And that's what this is going to study. Vector functions allow us to show how much the object moved and in what direction, and in a combination of some movement along the x-axis, some movement along the y-axis, and the combination of that is what makes like the movement of the whole thing. So first of all, a vector, you guys I think saw these last year in pre-calculus, because they asked me what should we put on there. So you saw that they exist and stuff like that. Here is me assuming that you've never seen them before and just giving you the highlights of what a vector is. So the main vector is an ordered pair on the xy plane, but the main difference is that we think of vectors as arrows instead of just points. Oh shoot. And they love these in science, I think, in physics, because they show like movement and magnitude and direction. So here's a point, here's a vector. Magnitude of vectors, this will become very, very, very important in a second. But a magnitude of a vector, have you guys heard this word? Hey, Jeremy. Do you remember what magnitude means? Yeah, it's like how big, how long it is. So the magnitude of a vector is simply the vector's length. And magnitude you'll see denoted in different ways, but this is the most common way, or at least in this class it is, with the absolute value bars. If you see absolute values of a vector, that means take the magnitude. Sometimes you see it with 2 absolute value bars, so you're like, no, for sure it's not a vector. But a lot of times they just do the single one. So get used to that. And then to find the magnitude of a vector, you guys could probably figure this out. If I gave you this vector, this red one, and let's just for simplicity say this is the vector 3, 4. Then what would the magnitude be? Nice. Nice. Yeah, that's it. This is just like a right triangle, so you do Pythagorean theorem like you didn't say. And you get 3 squared plus 4 squared, which would be 5 if you forgot those Pythagorean triplets. So in general, use the distance formula or whatever, the Pythagorean theorem, whatever you call it, that's how you find the magnitude of it. Cool. All right, so just very quick. Again, this will become important, but obviously they won't be this easy on the test. But real quick, find the magnitude of each of those just to make sure I taught you good. This is way more folks than I thought. So good job. Sorry again that we had to do it early in the morning, but it's only for 3 weeks. I think, let me check. Here's 1 week, here's 2 weeks, 3 and 2 days maybe. Okay, here's some answers if you want them. This should have been 25 plus 4, 54. No, it should have been 1. Are you guys good on that? Did you miss anything? Okay. Yeah, all right. Now, if you have questions, you can ask in a second. But yeah, it's just you're getting the length of it. This one should make sense that it's straight up 1. There's not much thought that goes into it. Here's the vector. It has a length of 1, and there's no diagonalness to it. So for sure, it's going to have a length of this component. Okay, then another simple thing just to like get you to see that vectors really aren't scary like that. But to add and subtract vectors, multiplying is its own thing. Actually, they got 2 different ways of defining multiplication in different contexts. But for adding and subtracting, it's very, very easy. You just take the x components and add them, and the y components and add them. So if you had these 2 vectors and you're trying to add them, you just do 2 plus -3 is -1. 10 plus 11 is 21, and that's your result. Again, that's kind of just to show you that vectors aren't scary, but also it kind of shows up in a second. When you like do an integral of a vector and then you put a plus c, you'll see how they do that in a second. Okay. Vector valued functions. These sound like they're scary. Oh my gosh, vectors and stuff like that. But they're not. In fact, you've already kind of seen vector valued functions. This is what I was talking about before. When objects move in 2 dimensions, they move both horizontally and vertically. Like here, I'm moving a combination of horizontal and vertical because I'm moving diagonal. So that's what goes here, horizontally and vertically. For this reason, when modeling 2D motion, we need parametric equations. One equation models the vertical movement, that would be the y equation, and then the other models the horizontal, that would be the x equation. And usually for motion problems, these parametric equations are presented as a vector. So what I mean is you saw these in 9.1 and 9.2. Now, instead of just writing them like x equals this and y equals this separately, they just put it together in a vector like x equals this and y equals this function. And sometimes they don't even do that. They still just write them separately. But sometimes they talk about like, give me the velocity vector of this thing. And this is what they mean. They basically mean take the derivative and put it as a vector. Cool. All right, then this is, I mean, just like if you're trying to think of vector functions, if these parametric equations made this red curve, then what a vector function would mean at any time, like for example, at t equals 0, that would mean take a vector from here and point it at the function, point it at the function, point it at the function, point it at the function. I don't really think there's anything worth discussing here. It's just a different way of thinking of them. Instead of as points on the graph, you think of them as vectors on the plane. But I mean, there's nothing, I don't think of them any differently than like a y equals x squared function. Cool. All right, then finally we get to the calculus, which is the interesting bit. And this says, what you would hope it says is that if you're trying to take the limit of a vector, if you're trying to take the derivative of a vector or an integral of the vector, you just take the limit of the x and the y or the derivative or the integral of the x and the y separately, and then put the answer in a new vector. So what I mean, oh, and then I put some fun ones on here. Well, not, I don't know if fun, but like good review on here. So like, for example, take the limit of this vector. Like I said, you're just going to take the limit of that dude, take the limit of this dude. And then put the answers as an x, y, like vector. So this first one, there's nothing interesting about it. It's just, can you plug in 3 without breaking any math rules, like dividing by 0 or something? Yeah, you can. So this would just be e to the 6th. There's the x component. But this one, we haven't taken limits in a while. Do you guys remember how you might do this? Because if I plug in 3 straight up, I get 0 over 0. What are you saying? Yeah, good job. Or you might have said L'Hopital's rule if anybody was thinking that. Yeah, but L'Hopital's rule, actually, that would have worked good. That would have worked good. But sometimes if this was like t to the 3rd and this was t squared, you'd have to do L'Hopital's rule like 2 or 3 times before you get an answer. Sometimes it's much easier just to factor it like on this. So I think I'll do that. This equals the limit as t goes to 3 of t plus 3 and t minus 3 over this. And then you smile because these cancel. And so now that equals the limit as t goes to 3 of t plus 3. Now you can plug in the 3, no problem, get 3 plus 3 equals 6. And so your final answer would just be this comma this in a vector. And I didn't really say, I don't know how you saw vectors last year, but here in this class and in a lot of classes, they usually use these pointy brackets. So if you see those, that means vector, not. Cool. All right, questions. All right, cool. Next one doesn't say find the derivative, but you can kind of guess. It says find the tangent vector to the function, to this derivative function when t is 3. So in other words, find v prime of 3, find the derivative at 3. And I'll show you why this is called the tangent vector once we get the answer. So let's actually, you guys do that real quick. Find v prime of 3. And then take this derivative, take that derivative, and plug in 3. Okay, you're trying to check your answer. It's on there. But this simplifies nicely because cosine of 3 pi over 2 is 0. So here's my final answer. And then you guys keep working on that if you want to. Let me show you what this means though. Okay, let me set this up. All right, watch this, watch this. Here's what this means. We got an answer of 0.6, was it? Okay. So here's the point I'm looking at, and it says find the tangent vector at this point. Okay, the vector 0.6. Well, here's when it's good to know like how much you saw last year. But last year, did you? Well, let me get there. All right, there's that point that we're interested in. We got an answer of 0.6, which is this vector right here. Woo, that vector. Okay, but did you see last year that like this vector right here is also 0.6? Like it doesn't matter where you put it on the plane. It's not like points, like it's a definite 5, whatever. With vectors, all that matters is like the direction and the magnitude. So this has the same direction and the same magnitude. So it's the same vector. This is still 0.6. Okay, so that's what we found is the tangent vector to this function. Meaning if this function were to like do this thing, boop, 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 then get to this point and continue in that direction, how far and in what direction would it go? And apparently, like according to our answer, it would go this direction for this long. You know what I mean? Like it would continue for 6 more units upward, straight up. Yes, makes sense.
That tangent vector before like hit something.
No, it's like if it was moving along this way at a certain speed, if it were to keep moving, whoop, it would go 6 units upward. Like if it were to continue in the same speed and same direction as it was going right at this point, it would go 6 units up in one period of time or whatever. Yes.
Wait, what do you mean by it? Like, how do we know it only goes 6 units up? What's the fighting?
In one, it would be like going, like just for easiness, let's call these miles. It would be going 6 miles per hour north at this point. Okay.
This is now applying a path, you could say.
Yeah, most of the time you'll see these vector functions as a path, as like a movement thing. All right, it's good. You convinced. All right, cool. All right, then let me delete these little arrows. There you go, and that's what tangent vector means. It's like tangent line. In fact, we can talk about tangent lines between these and tangent line in a second. That's the same idea. Tangent lines are like if you were to go on this function, then get to the point where you get the tangent line. If that function were to continue in the same direction, then what direction would that be? That's what a tangent line. Anyway, let's take this integral. Oh, let's take this integral because yeah, I get to see how much you remember about BC only. So take the integral of this. That just means take this integral and this integral. Second integral, I know you guys can all do. But this integral, actually, you're going to see this integral twice today because for your normal class, I have that integral in there too. But if you try to take this integral, you guys know the method. What would reverse chain rule would be U substitution, but I think you're thinking the right thing.
The one with like the DV.
Nice, yeah, that one. Yeah, that's called integration by parts, and that's the one you need. If you see function times function and U substitution won't work, like you don't see an inside function whose derivative is in there, then probably it's going to be integration by parts, and that looks like this. Remember, you choose a U, and actually you choose a U, du is then determined for you. And you kind of choose a dv, but not really. Like once you choose your U, everything else is determined for you. But these are the ones that you are picking out from the interval. Do you guys remember the strategy for choosing these? Like, how should you choose your U, or what should it be in this case?
The simpler one.
More like the one that gets simpler if you get the derivative. most of the time. You guys saw some exceptions to that already. But yeah, t, or in this case, u should be t because of what Annika said. If you take the derivative of this, it gets simpler. It just becomes 1 dt. Yeah, let me not even write the 1. Just straight up dt. And then the reason I was saying you kind of have a choice on the dv, but kind of don't, is because once you choose your u, then dv should be everything else in the integral. So in this case, e to the t dt should be your dv. And then if you don't know the antiderivative of this, then you did it wrong and you should swap your dv and your t. But in this case, I do know the antiderivative of e to the t is e to the t. Nice. And then you got to remember this formula by May 12th that for integration by parts, the result is going to be uv minus integral of d du. U, v, that's the u and that's the v, minus integral of v du. And make my u's more obvious there. Cool. Okay, and then you just take this integral, which now should be easier, or sometimes you have to do integration by parts twice. But eventually this integral should be like, you can do it, no worries. And you get this result, e to the t, nothing changed, minus integral of e to the t is just e to the t, and then plus the c, good job. Okay, the things will become important in a second, but then we also needed the integral of 9t squared. That one I know you know, it's just 3t cubed plus c. And so altogether, 8:26, and we have class 8:45. Okay, we have time. All right, so altogether, sorry, answer should be this, comma this. And then look at, you could put the plus c in here and the plus c in here. As I mean, you should call them C1 and C2 or something, or C and D or something. Or what people normally do is, you know how I told you that when you add vectors, you just add the x components and the y components. So what people normally do is like, here's my antiderivative vector plus a constant vector. So they put a plus constant vector here, where the c is a vector, like I said. So that c would comprise of the C1 and the C2. This c would be like C1, comma C2. So you can see that's this. You can see that's the same thing because this plus C1 from the plus C, and then that plus the C2. That's normally how you see it. Cool. All right, questions so far? Nice. Okay. Yeah, vectors, not super scary. They're just a different way of organizing stuff you already know. And limit derivatives, everything works the way you'd hope it would. It's just integral of the first and the second thing together. All right, let me circle this, and then we get to the biggest part, which is, remember I said you for sure are going to see this on the AP test. This is the thing that you'll see on the AP test, is they'll say a particle's moving, blah, 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 blah. And they'll ask you to do, they usually ask you these same 4 things or some small variation of those same 4 things. This one was from 2022 because I made this packet this worksheet in 2023. But if I looked on last year's, they would have a very, very similar question. All right, but first, please let us read through this. You tell me if you see anything that's brand new to you guys. First of all, position, you take the derivative, you get velocity, you take the derivative, you get acceleration. You already knew this, I hope. Okay. Speed is the absolute value of velocity. You already knew this? Yes. Displacement is this, which you guys just saw in Unit 8. Agreed? And distance is this with the absolute values, which you already saw in Unit 8. There's nothing new in here that you have to memorize, other than this part right here, Because remember, when it comes to absolute values of vectors, you guys remember what we talked about? The absolute value of a vector signifies what? You remember, Kim? Yeah, exactly. So here in your brain, like the picture that you see when they ask you find the speed of the particle, in your brain, you're still thinking, oh, absolute value, or at least for me, the picture that comes up is this picture right here. I think this comes up in my brain. But then I'm like, oh, wait, vector. So this means magnitude of the velocity. So since you're talking about vectors, that magnitude, which again is going to look ugly. It's going to be like x component squared. Actually, let me call it x prime just because we're talking about velocity plus y component squared. And actually, this formula should look really, really familiar if you were paying attention in 9.2. That's like the length of the path, and you can think about why that is later. But for now, just take my word for it. There's what that's talking about. For speed and for distance, you put this in an integral. As ugly and annoying as that looks, most of the time these are calculator problems anyway, so it does mostly do it for you. Cool. All right, with all that said, let's do this. You'll hopefully see, oh, this is no big deal. These should be 9 free points on the AP test. So watch this. A particle is moving along a plane, or sorry, along a curve in the xy plane, and it's at position this, x of t comma y of t, at time positive, like only positive times. The particle moves in such a way that the derivative of x is this and the derivative of y is this, and at time t equals 4, the particle is at 1, 5. Cool. Then it says find the slope of the line tangent to the path of the particle at time t equals 4. Okay. So slope of the line tangent to the path. When you hear slope, you see that word. What do you think you should do? Yeah, but there's a lot of derivatives. There's dx dt, there's dy dt, there's other derivatives that you missed actually. But yes, you should be thinking derivative. Which one specifically? Uh-huh. Oh, just straight up this dude.
Oh, that's all.
You kids with your hand idea. Yeah. Yeah, exactly. Slope is slope that you know and love. So if you weren't here, Jeremy, I forgot to record them, or like I didn't have time to set up the recording and everything. But slope is slope like in algebra 1. So change in y, rise over run. Change in y over change in x. So when it asks you for slope, you know they want change in y over change in x. Okay, they gave us dy dt and dx dt. So remember the way you get this. Actually, you remind me, how do I get dy dx when all I got is dy dt and dx dt? You remember, kid?
Put the dy dt over here.
Yeah, you just divide them. Change in y over change in x. So natural log of 2 plus t squared over square root of 1 plus t squared. Nice, nice, nice. And then you plug in 4 into this. Okay, so your answer would be natural log of 18 over square root of 7. The parentheses, by the way. Cool, there's the slope. That's all I wanted, slope. Okay, yep. Yeah.
I just need the calculator so I can really actually solve them.
You don't have to actually. You don't need the decimal for this. If you left it like this, they would be smiling, and if you did put that in the calculator, they smile at that too. Yeah. Yeah. Don't worry. Yeah. Don't simplify it in any way. It's better not to. Because if you're like, oh no, I learned that this is improper, I should rationalize it or whatever, and you do that wrong, even though you have this on your paper, they would pick up. That's not what, by the way, that's not what I do because I have too big a heart. So if I see this on your paper on a test, I like mark it right and I say, be careful with your simplification, but they would take up points. Was there another hand? Okay, nice. Okay, so slope, you already know slope. That's what I mean. It's like this is stuff that you already know. You just gotta manage like all the stuff that's already in your brain. Let's find the speed of the particle at 4 and find the acceleration vector of the particle at 4. Okay, we'll do that. There's 2 parts to this. First, let's do the speed. Say that again? No, well, kind of. But we just kind of talked about what speed is. There, the magnitude of the, oh, that's what you meant. Yeah, so it's the magnitude of velocity. Here's velocity, this comma this. And so therefore the magnitude would be this squared plus this squared. Well, square root of that. And then just to not take up a lot of room, although you guys have the whole back page is blank if you run out of room on this. The whole back page, like the back of this page. Anyway, but just to not take up a lot of room, let me plug in the 4 straight up into here already. So this would be 1 plus 4 squared squared. This is the SDT squared plus natural log of 2 plus 4 squared squared for the y part squared. Cool. And then, like I said, you can let them worry about checking if this is like, you don't have to take time to simplify this. But since we already know that this is square root of 17 and this is natural log of 18, you could do 17 plus natural log of 18 squared. But the thing is, if you're like, oh, let me be nice and simplify it for them so it's easier to grade, and you forget about this little squared like I almost just did, then you get points taken off, whereas you wouldn't if you had not been nice. Okay, so there's the speed. And then here's the acceleration. And then again, they're kind of nice and they give you hints in the language because they're like, find the acceleration vector. So then you're like, oh, okay, I know this has to be a vector. I know acceleration is just the derivative of velocity. So find the velocity of this, or sorry, the derivative of this and the derivative of this at 4 and put commas in between it. And there's your answer. If I were you, both of those are like manageable to do by hand. Actually, yeah, those are both manageable to do by hand. But if you didn't want to, this is a calculator problem. So you could put this into Desmos, and tell it take f prime at 4, take g prime at 4, and put that in a vector bracket. But like I said, these are manageable to do by hand. So let's do that with the 8 minutes we have left, and then we'll do C and D probably tomorrow. Yeah. All right. Derivative of this would be, well, this is 1 over 1 plus t squared to the 1/2. Bring the 1/2 down and then to the negative 1/2. I like to write that like this. Remember? But if you did 1/2 times this to the negative 1/2, that's also chill. But remember, this is a chain rule, so you got to leave the inside alone. So 1 plus t squared in the square root. And then there's still something missing from this. Do you guys know what it is? Yeah, what is it? Nice, nice, nice. So times the derivative of the inside, so times 2t, which let me just put that up here. Root 2t. And then similarly for the natural log function, the natural log function is just 1 over, leave the inside alone, times the derivative of the inside, which is 2t again. So let me put that 2t up there. Then let me put 4's where the t's are, and that's my answer. So a of 4, acceleration of 4, that looks like a 9, but that's an a, is equal to 8 over 2 square root of 17, comma, 8 over 18. Then again, you could simplify these, but you should. Nice. Y coordinate, that's a good one to stop at, but you can start thinking about C and D. Am I wrong? No, I'm right. Because 4, yeah, 4 plugged into this is 1 plus 16. All right, other questions?
Maybe I'm just tired. Where did the, for the Y one, where did the natural log go? Like in the derivative.
Because if you take the derivative, like if this had been natural log of t, then that would be 1 over t.
Okay.
But this is just 1 over, leave the inside, and then times the derivative.
Okay, thank you.
Other questions? Yeah,
I mean, it's for speed, so it's not like relevant, but would you, like, so I feel like for all of these, just because it's a 4-part question, you should plug it into like Desmos or whatever, plug in the equation. So it's like, would you find the integral of, like how would you find the integral of the factor? Like, would you just find the integral of both equations? But
yeah, this one might
then
be,
you have to do it at y6. Can't really do it. That's fine.
yeah, I mean, you'll see this tomorrow, so you guys can stop paying attention, but, yeah, if it wants the y coordinate at 6, so in other words, it wants y of 6. And so you need to take the antiderivative of y prime. So in other words, you have to do, well, you'll see this again tomorrow, but you could do y of 4, which is the one they gave you, plus the integral from 4 to 6 of y prime.
Oh, right.
It's this little trick that you see. Yeah, good job. Yeah, we'll do that tomorrow. Oh, you guys, good job. It spelled right. It's easier than competing over the AB people talking.